low in high dimensions. So starting with that is already quite easy. So it's not a difficulty here. And then what you have to do is now finding the neighboring ones that also have data points, the populated ones that are neighboring. And you have to do that efficiently. You don't want to do it linearly, because otherwise it's a nonlinear algorithm. And this can be done by storing all the populated cubes in an index structure, like a B tree. And then you have properties, because of the numbering scheme that you are using, to get easy access to the neighboring ones. And you have to connect them up. And then you can simply calculate the clusters. And like if you compare this, you see that you find kind of clusters compared to Birch. Birch is one of the typical clustering algorithms. You see that you find clusters, but given the percentage of noise, it's still like going down the percentage of clusters found. And the reason for that is that you may have this case, and you can easily imagine this is a perfect Gaussian distribution, but given my grid, you split the cluster. And in each of these cells, these 8 cells, you have only 1 point, at most 1 point. It's a perfect Gaussian cluster, but you wouldn't find it with our algorithm. And this is actually what happens here. The clusters are split, and you say, oh, it's unlikely. It's not that unlikely in high-dimensional space. It does happen. So what can we do here? And like I'm skipping some of the details, but we do another algorithm, the OptiGrid algorithm, which is doing a recursive partitioning based on contracting projections, determining some cutting planes through the data that are not cutting through any of the clusters. Basically, we are now not cutting regularly in a grid, but have an arbitrary grid. So you never cut through a cluster. That's the idea. And then we use a generalized